Today we are doing 10.5. I have 10.6 in here because it's basically just making inferences, but with different things. We're gonna first make inferences with surveys, and then we're gonna make an inference with an experiment. So 10.5 is making inferences with surveys, and we actually get to do a little bit of math now today. Great, amazing, right? So the past 3 days, the past 3 lessons, not 3 days, 3 lessons, we've been remembering a bunch of vocabulary about cluster sample and all that stuff. Now we actually get to do the math. But first, we do have to still remember some of the vocabulary. So we have descriptive statistics and inferential statistics. Those are two different things. For example, the descriptive statistics, what you've been doing, you find the mean, you will find the standard deviation, and you normally use it for a population. You normally infer stuff out of a population, which then has the sign of the Greek symbol of mu for a population mean. However, a sample mean is x with a line through it, or the sample. You normally collect samples in inferential statistics. You collect the sample and then you make inferences based on that sample to the whole population. So it's not descriptive statistics; it's more inferential statistics. And the sample mean is x with a line through it, which basically is the population mean, the sum of all the data points divided by the number of data points. So, before we do this, everything else in this chapter is really just common sense, except this. This is a margin of error formula, and it's approximated by this formula. It's 1 over the square root of n, plus or minus, right? So, for example, if you have 4 people in your 4 people in your sample, margin of error. So for n equals 4, margin of error is 1 over square root of 4, which is 1 over 2, which is roughly 50% plus or minus, which basically means it's extremely inaccurate. If your n is, I don't know, 3600, you'll have plus or minus 1 over square root of 3600, which is plus or minus 1 over 60, which is a margin of error of around 1.67%, which is a lot better than the 50% you're not accustomed to, that you get when you only do 4 people, right? So that's the margin of error. And we're gonna go through some examples. I'm only gonna go through 3 examples today. We actually have to do some math, so I'm not going to just race through all the questions like in 10.2 to 10.4. 9. Modeling with mathematics. National polling company claims that 54% of U.S. adults are married. 54% of U.S. adults are married. So you survey a random sample of 50 adults. So what can you conclude about the accuracy of the 0.54 when the 31 adults in your survey are married? 31. So 31 divided by 50 is equal to roughly 0.62, which means 62%. So 62% and 54% they're not that much different from each other, unless if you live in a different place. U.S. adults might be more likely to be married, for example, Florida, or places where a lot of old people live. They're more likely to be married. Whereas if you live in Lawrence, Kansas, college town, there's no one married there because, well, Lawrence, Kansas, and there's a university there, so most of the students are college students. 19 adults. 19 adults will get you 19 over 50, which is about 0.38. So this is an even bigger variation. So the accuracy of the claim, it depends on the thing. It depends on where you are, your biases, but generally the 54% claim, if it was all fair and dandy, 54% claim is not to accurate for the 38%. However, we have C now. Assume the true population proportion is 0.54. Estimate the variation among sample proportions for sample size 50. So now we can use the margin of error calculation. However, it says estimate, so we could estimate, but we're just going to use the margin of error calculations anyways to try to see if these numbers are justifiable, right? So try to see if we can have this 62%, which is 8% away. So let's do the math. 62 minus 54 equal 8, and this is 62 minus no, this is 38 minus 54 is minus 16. Right, so we'll do the 1 over square root of 50, which is roughly equal to 1 over, let's take the lower end, no, let's take a higher end. So this is definitely higher, no, should we take the higher end? Yeah, wait, no. So we'll just take this 1 over square root we'll take the lower end, 1 over square root of 49, right? So this is definitely smaller than 1 over square root of 49. That means this is a more accurate margin of error. And then this would be about this would be exactly 1 over 7, not about, and it would be about 14.29%. 14.29% margin of error, plus or minus. So we take this 14.29%, and we compare with these two. This is justifiable, right? The 8%, there might be differences in the amount of adults that you sample. However, in this one, this is not justifiable because it's out of the margin of error, right? And that's a really big margin of error, right? So if it's this is a really big margin of error, so this is way out of even that big margin of error, then you can conclude that this isn't really an accurate this isn't really an accurate, either this isn't an accurate claim or your experiment's flawed, your survey's flawed, right? Next example, 22. The figure shows the distribution of sample proportions from 3 simulations of 3 using different sample sizes, and which simulation has the least margin of error, and which simulation has the greatest margin of error, and explain your reason. So, these simulations, these all look like bell curves. They all look like regular bell curves. Which simulation has the least margin of error? Margin of error actually has to do with standard deviation, right? The higher the standard deviation, the higher the margin of error. Lower the standard deviation, the lower the margin of error. So basically, if we're talking about let's say the C, if we're talking about the C, we'll see that a lot of the stuff is way out. See, we'll see that a lot of the data points are still way out of the mean, right? The mean is 50. They're way off the mean. We still got like a pretty decent number of data points at 60%, whereas B, that kind of ends at 55, and then at A it kind of ends at 52.5. So C basically has the highest standard deviation, therefore C has the highest margin of error, and then we have B, and then we have A at lowest, right? So sometimes you can just look at the graph and then you would know which has the biggest margin of error. And because A does not have a big margin of error, I'm guessing that A has the highest amount of the biggest sample size, and then B has the middle, and then C has the lowest. Example 3, attending to precision in a survey of 1,022 adults, 76% say that more emphasis should be placed on producing domestic energy from solar power. What's the margin of error? So it's just a regular standard margin of error calculation. That's easy, plus or minus the square root of or 1 over the square root of 1022. Is that even in it? Yes, it is. So let's take this as a round, because I'm too lazy to pull out the calculator. Plus or minus the square root of 1024, which is equal to 1 over 32, which is around 3.06% either way. 3.06% either way. Right? 062503. No. Wait. Yeah, no. It's not 3.06. It's 3.13% either way. Right? So what's the margin of error? 3.13 plus or minus. Given an interval that's likely to contain the exact percent of all US adults, we think more emphasis should be placed on producing domestic energy from solar power. So that's the surveyed, and this is the margin of error. So we can just take the interval is plus or minus this, so that's 79.13, and then the lower bound is 72.87, right, to 79.13. So if we have, I don't know, a graph of 0 to 100%, and then we have, I don't know, 70s right there, so 72.87%, and then that's 79.13%. So the percent of all US adults is likely to fall in this margin. Right here, it can be exactly 76, but it's probably not going to be. Right? And it's 1 over square root of 1022, so the margin of error is a little bigger than that probably. But that's what you gotta do, what you gotta do. So that's gonna be it for 10.5. See you next time for the last lesson of 10.6, which is making inferences with sample experiments. Experiments, not sample experiments.